So I had to split this up into two parts because it's not scripted. So, and it's taking a while. So let's go over where we are and what we're doing. So essentially, we have a return address here. The very top return address, and this returns to the CRT because we have our main function, right? Then we have some unknown amount of data, and then we will have our 4 parameters or our 4 stack locations that are reserved for our, this is the return address back to main. Return for our call down to the test entry point or entry function, TEF, I guess you could say. So we call from main into TEF. We have 4 parameters here. This does what it needs to do. But what he wants to do is, instead of returning back up, essentially, let me draw this a little bit further down. So what he wants to do is that main goes down into TEF, the test entry function, and test entry function wants to return into the test inception function, and test inception function wants to go into the test inception EX2, which wants to go back up to main, for example. But getting beside myself there. So in order for him to return up to the inception function, though, we need to do a couple of things here. First is we want to save the return back to main. And so what we're going to do is take this main and then move it up to here. So essentially, now we're going to have this stack that's over here. Actually, let me, so we have more room. So this is to the CRT. So now we have, again, to the ret to the CRT. We have some unknowns here, and then we have main ret. And then we have that, and that. So first thing we're going to do is return to the shim functions. The shim functions do nothing, and so return from him to shim. And shims do nothing but return. So essentially we're just going to go up the stack until we're up to here. Now the thing is that this location is unaligned. This is aligned. This is unaligned. This is aligned. This is unaligned. I want to be at an unaligned location whenever we enter the functions, because the functions will align themselves. So they're expecting to be unaligned. And if we do that, we can get back on track. So what we're going to do here, over here is shim, 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 test inception. So shim returns to shim, returns to shim, returns to test inception here. And test inception is now at this location here, with return to main. And so he thinks he owns these parameters. So hopefully the compiler won't generate anything to touch them, because it could really mess things up if he does touch them. But anyhow, within test inception, he will now have his own stack base below now. All these are all gone, so he owns his own stack base below. He will do some alignment. And now we're going to call, in order to regenerate, because we need to regenerate 1, 2, 3, 4 stack locations and this to return. So we need to call a second function, which is now the test intercept 2. And so when we do that, we have 4, 3, 2, 1, and then the return, and then some stuff here. And so now we've gone down into here. So essentially we want these two to line up. Now we do have this unknown bit of space right there. So what he's going to have to do is he's going to find his own return address. He's going to replace it with shim, and then he's going to find wherever that location is on this side and copy main to it. And then he's just going to keep replacing shim all the way up until he hits main. And so you have shim, 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 whatever, however many it takes to get the main function, and then he'll return back up to main, and then main will then call thread exit, and it'll print the return, which will now be garbage. So this is the first thing we're finishing here. The second thing we might take a look at would be, is it possible to maintain the, well, right here, test entries. This is, let's say text exit. Test entries, return value. Now, if I manually in this function store it somewhere, I can sort it down the stack at a fixed location. I mean, all kind of things I could try to do, pass it around. So sure, I could do that. But the problem is, that's kind of cheating, right? I want to only manipulate it after it returns. So can I find that return address, or can I get to it? So just think about it. Now, so you're entering in your main function, and you want to get the return address. It's like this. It's like if you entered into main, or but bad example here. So we'll say with function xyz. xyz calls create thread, and it returns a handle. Then it calls this other function setup. Okay? And setup isn't passed anything. Or maybe it is, but x for return from this is separate. And within setup, I want to get the return of create thread. Within setup, it was never passed it. That's essentially what we're trying to do when we get this return value back from that. How do we get it? What will be a way to get it? And so that's what we're also going to explore once we have this whole thing sorted out and working. We'll review that, and then we will work on the return value. You know, I always mix up saying return value and return address sometimes, but we will see if we can get the return value after we return from a function as an entry point to another function, right? So we're entering into a function, and we're going to see if we can get the return address or the return value from another function. It's not stored anymore, it's stored in a register. And that register can be used at any time and overwritten. So we'll see what we can do. All right, so we were going to take a look here. So again, we have everything made up. So it pretty much should work now. So we can do a compile here. Then let's do a test here. And then we'll go through it. We'll step through it. Okay, so let's just step through this thing now. So it looks like it's working because we have test entry, intercept, exit. Now the exit parameter is wrong, but we'll get to that in a minute. Let's go to main. So the first thing we're going to do here is we're bypassing the compiler stuff. So we're going to go to test entry. Let's remember here that this is our return address. These are our 4 locations on the stack. Okay? So we're going to hit that, DQS, that, L5. Oops, not 54, 5. Okay, so we have our return and 4 parameters, right? Now we are going to come through here. Now we're going to grab this here. So this one here is ED, right? So 2ED, 2ED. So it's grabbing this here. It's grabbing main for the return address to save it. And what's it going to do? At the end, it's going to move it up here, right? So we've grabbed main, and main is an RAX. Right, so we're gets back to main. And let's rearrange the code a bit because it is moving it to 28, the exit function. So it's moving it to exit function. So it's using the stack as a local variable. So this is the thing about when we're talking about the compiler. Compiler can use these for anything it wants, right? But it's still in our REX anyways. So now we're going to put our CX, which is our test shim. Let's do this. Let's see where it goes. And put the test shim as our first parameter. Now put it as a second parameter. Now notice what happened. It overwrote where the local variable for this was stored. But we're getting lucky here because it's still in REX. Now it's not in REX anymore. However, what happened up here what does RCX have? RCX has that. And then we're moving that to the top. So main has been moved to the top now. Just after, luckily, after we overrode this one. Now the next thing to do is to put the test intercept into that location. As you can see, it's all been set up like we wanted. So now we're going to do the printf. And we're returning REX dead beef. Don't worry about that for now. So we're returning to shim. We're in shim, returning to shim. Now return to testing exception. Now in testing exception, you know that this is the actual last thing we're allowed to really use. So we hope that the compiler doesn't try to use these parameters here because these don't belong to it. And this is not his real return address. We've just put this there to save it. So now what we're going to do is call the get location and we're passing in. So now what we're doing is so notice what else happened here. So if you notice, this was a 1 here. Luckily, they're not using it for anything besides alignment, because this turned it into a negative D word 1. So it actually used it. So if you see RCX, which is negative 1, was actually stored there because it thinks it was a parameter. But the only thing we would do with that parameter is use its address to get to the stack. So unfortunately, we did kill something we shouldn't have in this main startup function. Shouldn't have killed that. But it's not used. Should be used, so should be fine. But you can see that we've killed that, even though we shouldn't have. And now we're going to go down here, and an RCX is going to give us the address so that we can now, whoops, stepped over it. It's okay. I do that all the time. Okay, let's go back in this thing. So, as you can see, we are now in the exception x2. We're going to do some stack stuff, and our return address is there. We've got 1, 2, 3, 4 on the stack. We have an alignment, which is the black stuff. We don't know what that is. Then we have the top, where it says the original return address, and we have the pointer to that. And then there's stuff we shouldn't touch, which we've already touched. That's been ruined. So what are we going to do? Well, we move this down to the real location, right? Because we had 1, 2, 3, 4. These are the parameters that we don't care about. Our home. We will return will be at this location in the main function, and they can return. So we want to be able to return to here. So what we're going to do now is from our return, we're going to fill up. I think our return might actually be here. Because we have this inception, and we have 1, 2, 3, 4, right? And so then this is actually our return. So we're going to override these two with the shim. Fairly straightforward. Override shim, override shim. Right, so we got the shims with the main, and that's it. We're going to print that we're in this. We're going to extract up our stack. Then we're going to return twice to shims and go back to main. And as you can see, 58 hex is what was returned from printf. See, printf before Rx was that, and now it is 58, which is 58 to decimal is 88. And that's what's going to happen when we get print. So we end up back in main, and then we call the exit function. We print that, and so we have been able to do this full intercept, right? We've been able to, come in here, call our entry function, print, have this interception function print, and then return back to main, mostly uncompromised. But as you can see, we did have one casualty, but it doesn't matter because it's not used. Now what we do miss is dead beef, right? We don't have it. So part of this question is the problem with that without doing assembly. Even without doing assembly with doing all C code, we still mess things up. We overwrote something in main that we shouldn't have. Again, because we're not in control of the low level here. We're only, we can manipulate certain things, but we have no control over what actually goes where and how the compiler optimizes. So once we start doing things that creates an area that is out of bounds in reality, the compiler, by definition of how those functions are supposed to work, is not out of bounds. It can use it. And so that's how we got that -1 D word corruption. Doesn't matter though, because no one uses that value. In fact, let's see here. Once we get back here, do we even populate it with anything? No. Well, actually, that's interesting. That -1 was actually a saved value for RDI. So we actually did corrupt a non-volatile register for the function main CRT startup that called main. So actually it wasn't just for alignment, it was actually also saving a value. So we actually did make an oopsie. But we're just messing around here. This isn't something we're supposed to do. The idea of this exercise is to get you more familiar with how the stack works, how things work at the low level, so you can debug problems that go off into the weeds like this. Because as you can see, the compiler won't do some of these things,
right? I mean, the compiler's not going to do these things. But your program, the way you write your code, can end up corrupting things in ways that you don't realize. So luckily, doesn't seem to care. I mean, it doesn't even use it after it comes up. Just calls exit. So it's not even going to use it. It was just being saved because main used it. Main has no idea what actually the caller is using. He just knows that it's non-volatile. He corrupts it, so he must save it. Luckily, it was not being used. So there was no crash. This actually worked fine. Now let's go back to the variable. You know, this is harder to do without. As you can see, we've already been corrupting things everywhere. So um, essentially, once we get into inception, that's the place where we know it will be there, right? So if we go back into the program, stack program, test, inception, REX is dead beef. That's the return location. Now, is REX modified here? Well, when we call get proc address, it will then use that to call REX. Or use that, if the return value is in REX, it will use that. So that's the time when it comes corrupted. During this function call and on the return. Now, one thing you may not know is gotos aren't scoped. If p return location does not equal 0, goto get return, preserve return. Okay. Preserve return. So let's see if that's true still. And if this code doesn't change, and it just jumps here, and it just uses REX, we should still see dead beef, which means we may have a chance to save dead beef. So let's give that a try. Okay. Oh, nope. Maybe. Where does it go? J not equal D1. Oh no. So goto has now outsmarted us. So what happens here is that if this is not 0, it will jump to 3D1. 3D1 is here. And it's going to move RBX, RSP plus 30. And then it's going to move that in RDX and go for def. But if you went this path, it's actually going to use REX and then jump to 3D6. Oh, 3D6, not E. So it's going to jump to 3D6 and then move REX and RDX. So essentially, you're going to get garbage. Whatever's at RSP plus 30. It'll never actually store it there, but the compiler, and again, the compiler is now going to use that all the time. if it has to store it. But see here now it knows it's an RBX. So essentially it's using the first parameter as a storage for it. So again, we have to trick the compiler somehow to give it to us. If the compiler would have just not done this little trick and just followed to here and copied it over, we'd be fine. But the compiler is not doing that. So, so again, the thing is we can reserve it. We can easily just put it somewhere, just like we did the return address. But the question is, could we get it without doing that? And yeah, it seems like it's going to be hard to get it. But I have another idea. Test shim is void. What if test shim was uint given test trick? Could we get it done? Don't do this nonsense. Do we think? Test trick. pfn test trick. So what we're doing is we're actually typecasting a void function into one that returns something. And since that function does nothing but ret, could we get that return address or that return value from this? Yep, it actually built. Surprise, surprise. Oops. Passing in the... It doesn't matter. No parameters anyway. Nope. Did not work. All right, so test inception. Oh, no wonder. I forgot to do this. Oh, look at that. We got it. Remember how to do dead void here? Uint. Uint return value. Can we pass this through without messing it up though? Return value. All right, so uint return value. So, question is, will this still work? Will we be able to get this on through here? And will it not mess up something on the stack? Because if it messes up something on the stack, that's another big problem. And we need to get this before we call this, for sure. And then up here, we need to change inception to. Of course. Well, so to change inception to that. Oh, and that. Okay. Okay. So now let's go in there and take a look. So take a look at test inception. Ooh, we got our dead beef. Well, here's the thing. Okay, we haven't messed up anything up here, it looks like. So, looks fine. Will we be able to return it? We're returning it. Ooh. Teshim, ret. 1, 2, 3, 4. We did it. Oh, we messed up somewhere. Thought we did anyways. Oh, right there's dead beef. Okay. So, what ended up happening is they took one of our storage locations to save dead beef. Right at the end here. So I was wrong at where the... Wait a minute, we're at... So what happened here then? Let's try this again. So our ask is dead beef. And we're going to do test shim, return. That's it. Oh! I see what the problem is. RBX was destroyed. RBX is dead beef. And why that happened is because we never returned back up to the previous function to clean up. So let's see. So what happened is this exit function here was stored in RBX. And so when it gets back here, it's going to return and recall RBX. Now, whenever we overrode these things, whenever it came into here, it stored this return value in RBX. So it would pass over this and go to here. So that's the problem, is that that was stored in a register that was now overwritten. And since we don't come down here, we don't restore it. So that ends up being an issue, obviously. Now, let's just say I said volatile here. If I say volatile, it has to put it into the But who knows where it's going to put it. Oh, nice. Still mess it up. Oh no, we actually got to the exit function this time. Except now it overwrote the second parameter. So it's saving it on the stack as a second parameter now. Since I don't care about this, what if I just did this? Stored it there. Pass that in. Got rid of the return value here. Doing everything we can. Because I already know that it's going to overwrite the top stack location, but we don't care. Because we know it's not being used. It's saving a register, it sucks. You know, we're not really supposed to do that, but, you know. Oh. Oh. I'll get this to you long. 64. Just turn it into. Just save it directly in the location. Guess it's not a pointer anyways. Alright. 109. Oh. You long. You long. Okay. Okay, so worked. So there you have it. We have been able to not only hijack it, but intercept the return. Which, again, this is not. It's a lot of it's luck because we're just messing around. And if you compile this on your system, it may not work. Because it depends on where it's optimizing everything, where it's putting everything. So, so let's go back down to just one more stepping through. Interception. Okay. So here we have dead beef. We come through. We call test shim, which does absolutely nothing. And thus, since we've typecast a void, which does not touch REX at all, we don't return anything, right? I mean, in this thing here, we return nothing. We don't do anything. I don't even need to put that return in there. We're not doing anything. It preserves REX, and since we haven't touched it yet, now we end up saving it, you know, in a place we shouldn't, but it is what it is. We know it's not hurting anything in this particular situation. Other situations, it could be. It probably would be. And so now we've been able to pass in, you know, dead beef in the second parameter, and in this parameter here, we've passed in the thing we were written, but more importantly, we now have the location that we need. Right, so now we fix everything up. As you can see, we are putting our test shims in. And here we're returning from this with dead beef, returning from the shim, return from the shim, returned to main. RBX is preserved since we forced it into the location, so it's still exit function. And so there you have it. We can call test entry, test intercept, text execution, and still display the return address or the return value from test entry by preserving it in a big hacky way. It was real time. I just planned the idea. I didn't actually plan how I would do it or anything like that. So, well, this is a long video. Hopefully that you learned something here. Essentially, how function calls work, how we manipulate the stack. Like I said, this is not teaching you how to program. It's teaching you, how things are working underneath and how you can manipulate things. How the compiler is working, how the compiler is optimizing things, and how you can try and get around things. So it's not things you use, but it's good to understand how things work. Okay, so anyhow, that's it for this video.